Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 27 of this course on machine learning for earth system science. Today we are going to begin module 4 and the topic of this module is machine learning for earth observation systems. So, earth observation systems is the network of satellites, sensors and all the measurement devices that have been deployed extensively over land, over ocean and also in the space through spaceborne vehicles, and these devices they keep on sending a huge volume of data of various forms to the ground stations. So, these huge volumes of data they can be these can be in situ measurements of say temperature or maybe other properties of the land or of the sea, or it could also be like various photography captured from the air. There are satellites, radars and all these kinds of devices which which basically capture imagery. These imagery need not be the kind of images that we are familiar with in computers, but they are they have their own technology by which they send in some signal, and then as that signal is reflected back they try to capture that reflected signal, and on the basis of the intensity of the reflection they form some kind of a image like structure, and based on such reflections it may be possible to make some measurements about the the field on which they are focusing. So, what we are going to do in this module is we will see how useful information can be captured or can be extracted from this vast volume of data that is being generated by earth observation systems. The major focus will of course lie on the satellite and radar imagery, and because these are images we will see if the parallel progress that has taken place in the domain of computer vision, image processing etc., if some of the algorithms used in these fields can be applied in this in the case of remote sensing imagery. And many of the algorithms that have been developed of late for computer vision or image processing, where the task is to look at normal images which are, let us say, captured by human beings and put up on social media and things like that. Much of contemporary computer vision is about interpreting those kinds of images, as we may have discussed in some of the earlier lectures, and the most successful methods used in computer vision are deep learning models such as convolutional neural network and so on. So, the aim of this module will be to explore how these methodologies or how these models may be used to extract meaningful information out of the remote sensing imagery. So, the basic concepts that we are going to cover today is deep learning architectures for object detections, challenges of object detection in satellite imagery, and adapting object detection frameworks for remote sensing. So, object detection we know is one of the standard tasks in computer vision. So, let us say this is a standard image in which as you can see there is a field on which 3 sheep and 1 dog are moving. So, that the target is to detect the different objects that are present in the image. So, in this case you can see that there are actually two apart from the background grass there are 2 classes of objects, or we can say broadly we can say there is one class of object, the animals. Then within the animal class there are again subdivisions, this dog and sheep, and then for sheep again there are 3 instances. So, first there is like the broad level category of objects, then there are like or more fine grained categories of objects, and then for each category of objects there can be multiple instances. And so now, so this is a normal image that we that computer vision typically deals with. Now, if you look at these images, these are aerial images maybe taken from some helicopter or something like that over, as you can see, over a port or over a parking lot. So, this port has like lots of boats parked one at a time. So, the task might be first of all to detect the port, that is like, or to detect this series of vehicles that are parked here, or it can also be to detect the individual boats. Like for example, I may be interested in counting how many cars are currently parked in the parking lot. Is there overcrowding? Is there space to park some more vehicles, and so on. So, to do this in an automated manner, I need to like actually detect each individual car, and so that I can count their number. So, in any object detection problem, the challenges are shape, scale, orientation and various other properties of the objects, which may vary from one image to another. So, like in this case, like we can see that the dog is here and its size is something like this, but in another image, like that image may focus entirely on the dog. So, the whole image can be focused around the dog only, in which case its shape and scale will be very different. Or orientation. In this case, like we are seeing their side views, but we could also see their front views. Their front views, like these objects could look very different from like when viewed from the front or from the top. So, like all these properties can vary from image to image, and to learn a representation of a particular class of objects such as dog, sheep, boat or car, one has to build a representation that is either robust to multiple to different shapes, scales, orientations, etc., or like we have to have an ensemble of models like for that is, or ensemble of representations, one for one orientation, another for another orientation, and so on. So, but representation of these visual properties is itself a challenging task. So, earlier like in classical image processing computer vision, like like we used to have features inspired by signal processing. Now, of course, we do not do that. So, those features are sometimes now referred to as handcrafted features. Now, computer vision community has moved away from those features. Nowadays, they use mostly neural features which are automatically learned by neural networks. So, that has removed the feature representation problem, but the neural features that are learned, whether they are actually able to represent all the like variations of the properties of the object, that is an open question, and it may vary from one application to another. And then of course, there are some secular challenges which are irrespective of the method you used. So, these are like occlusions, shadows, etc. That by occlusion I mean that the thing or the object which you are trying to detect, that may be partially or fully covered by another different object, or there might be shadows which like if a shadow of a tree falls, then this white sheep that can be look blackish, or then that can kind of these kinds of occlusions and shadow, they can really mess up with any object detection methodology. Now, coming to some of the rather well known methods for object detection which have been used of late in computer vision. So, one is the RCNN, the regional convolutional neural network. So, in a like when we are doing the object detection in any image, the most like one of the biggest challenges is first of all to localize where the object may be, and secondly and next to understand whether the object is there or not. So, like here is an image like let us talk about this image. So, here we are, let us say we are looking for a person. So, the person, as you can see, is located in this part of the image. But how do I know that it is really this part of the image that I should focus on? Why not say this part or this part or this part or any other part? So, what RCNN does is, first of all it passes the image through a series of convolution layers just like any CNN, so that we have a like a neural representation of the of the image. The next important thing which happens in RCNN, which is different from other neural networks, is the regional proposal network. So, it proposes something like a regionalization of the image, like a person is located here, other things are located, or I mean not necessarily person, but the target class is located here and the other things or other objects may be located in something else, or the target object may be located here, other objects may be located somewhere else. So, these are all proposals, and each proposal needs to be evaluated whether that particular regionalization makes any sense or not as far as this image is concerned. So, what the region proposal network does is, first it proposes a regionalization, then on each of the regions that it has proposed, the object detector works, which is basically something like a classifier. The classifier tries to classify each region of the image whether it belongs to the target class or not. That is, if this region of the image, if this is a region proposed, then the classifier will try to classify this region as person or non-person, and it will say hopefully it will say non-person. Then that like we may choose to reject that proposal. Then another proposal will focus on this region, and then it will like again will try to classify, is this person or not person, again it will say not person, so we will reject it. Then we may focus on this region might be proposed by the network, and here the classifier will run, and then it will say that yes, it is a person. So, like we can say it will be accepted. Then similarly, like other overlapping regions involving the person, they may be evaluated, classified, and like then all these things, like all the regions that have been accepted, they will somehow be pooled together. So, there is an ROI pooling layer. So, region of interest, ROI stands for region of interest. So, the different regions of interest will be evaluated and then pooled together to form a single representation, and that thing is next going to be passed through another neural or some other neural layers. So that the final output will be one, the that is the output, whether the binary output, whether the target class is present or not, that is in this case a person is present on the image or not, and if so, then what is the bounding box. So, there is a bounding box regressor. So, this is a regression problem of predicting the boundaries or the corner coordinates of the bounding box. So, that is how this whole thing, this RCNN works. Alternatively, there is another deep learning based frameworks called YOLO, you only look once. So, like unlike RCNN, which creates multiple proposals and evaluates each of them and maybe discards some of them, keeps some of them, etc. YOLO, the idea is that there are no multiple things, there is only like you do the whole thing at one shot. You basically at one shot you divide the image into a large number of regions, sub-regions and so on. You can say a hierarchy of regions, and then each of those regions are going to be like classified at the same time as object or non-object. That is to say, like we can say in each of the grids into which the region has been divided, the classifier will try to predict the class probability, whether that this region belongs to the target class or not. And so, like we will get something like a class probability map. So, for different levels of like as I mentioned, there is a hierarchy of this regionalizations. Now, for every particular regionalization, we will get a class probability map like this, which will somehow be all combined together to form a final detection or I mean to say to find the final bounding boxes or not. And now this is normal object detection. Now let us talk about remote sensing. So the same object detection problem we want to use not on ordinary images which we capture with our cameras, but which are captured by captured through remote sensing. So now if we want to use object detection on the remote sensing imagery, first of all let us look at what are the kinds of remote sensing imagery. So images are captured by, they may be captured by satellites, radars, drones, aeroplanes and so on. There can be more sources of remote sensing data. Now these images they can be captured at different wavelengths, spatial resolutions as well as using technologies. So the wavelength, like as we know there is the electromagnetic spectrum, a part of it is visible to the human eyes, other parts are not visible. By that I mean that there are certain wavelengths, and at certain like if the images are captured within some wavelengths, we can say that they lie within the visual range. That is, by looking at those images we can understand that okay, this is a car, here is a car, here is a tree, here is a human being, etc., etc. But in other wavelengths we may not be able to, that is by looking at them we may not be able to make much sense of it. So there are basically four major types: the visible images, infrared images, hyperspectral and multispectral images. So the visible image, as we know, like it sometimes also can be called as RGB images. So there is a red channel, green channel and blue channel. So these are actually different wavelengths or a set of wavelengths within the visual range of the spectrum. But then there is infrared images, which is of course, which means at a lower frequency than the red wavelength, so to say. And then there are hyperspectral and multispectral image. So a hyperspectral image is something is such an image where the capturing is done at many wavelengths, or we can say at a series of wavelengths which within a single spectral band. So let us say that the entire spectrum can be divided into several blocks, and we focus on one particular block. Just for saying, let us say like 30 to 50, let us say this is one block. So within that there are so many wavelengths are possible. So we choose that is, we do the image capturing at like at a very large number of wavelengths within that block. That is called, and the set of images we get like that, that is called a hyperspectral image. So like it can be represented as a cube, that is at each wavelength we are getting a 2D image, but then there is a long sequence of images like that, each at a different wavelength. So taken together they form something like a cube. Then there is multispectral images. So this is captured at a few wavelengths, but that are across the spectrum. So like unlike the hyperspectral images where all the wavelengths are within a particular block, here the different wavelengths are spread across the spectrum, but they are relatively few in number. So multispectral and hyperspectral, we can say they are complementary to each other. And so, but now all of these can be these are sometimes referred to as passive sensing. Now there is something called active sensing also, where like the active in the sense that the device actually sends some signal and then measures how much of that signal is reflected. So in the passive case, the device does not send any signal, it merely tries to capture how whatever light etc. is reaching it. Now in case of among active sensing, there is this synthetic aperture radar or SAR technology, which basically measures the reflection of the emitted energy. Now when we are doing remote object detection or remote sensing, or for that matter any other problem on remote sensing imagery, these are some of the problems we face. So first of all, the pixel value properties might be different from standard images. So we know that in standard images, like there is an R channel, G channel, B channel, each of the pixels, they have a value between 0 to 255, which somehow indicates how red they are or how green they are or how blue they are. If it is a grayscale image, it means either how black it is, or how dark it is or how bright it is, and so on. In this case, like these pixel properties, they may be different. depending on the sensing technology used, the spectrum used and so on. And as a result, the way the responses of the different filters and so on which we are which we use in standard imagery, for those filters may not be very suitable for in this domain or on these kinds of imagery. Then when it comes to object detection, so first of all there is a small size of the objects to be detected, because if they are taken from the top, like if you want to do a ship detection or car detection from the top, obviously it will be of small size, and their shapes may also be hidden away if we are taking a top view. Now also another problem is that there is a small number of labeled images which are available for training. Because these images are difficult to capture, or even if they are not difficult, even if the modern technology can capture lots of these images, but the big challenge is labeling them. That is, who will actually sit and do the labeling of all the images, that is this image contains such and such objects, and then localize those. So that is a very tedious task. So some of the approaches which are taken to alleviate some of these problems. So sometimes what we do is like on the standard detection architectures which we talked about earlier, RCNN, YOLO, etc. we just make some suitable modification for the domain and use them. Another thing that is often done regarding the problem of small number of labeled images, now we take reasonably small size of imagery, but then each image we split into many sub images and use them for training. So instead of capture like a normal neural network for used for computer vision, they are usually trained on millions of images, but in this case it is of course very difficult or impossible to collect millions of images and annotate them. So what is done is a manageable number of images, let us say a few hundreds or at most a few thousand images are collected, they are labeled, and then those labeled images they are split into multiple sub images, and each sub image is used for training purpose. And now and sometimes also domain adaptation is used from one region to another. And finally we combine the images from multiple sources to get some kind of an unified representation. That is like we may go like use the images of the same phenomena or the same region captured by, let us say, 3 different satellites or a satellite and radar and so on, and then somehow we combine all those together to now the reason for doing that is that the satellite image may have certain properties like which the radar image may not have, or the hyperspectral image may have certain properties which the multispectral image may not have, and vice versa. So like if we do the detection separately on the different images, maybe in some images it will or like the images from one source or one technology, it might be the object may be easier to detect, in the other it may not be so easy to detect. So what we do is we do something like fusion. So either we treat all the images from the different sources independently, do the detection in each of them, and bring and then combine their results somehow, or we combine the images themselves from the different sources and do something like something known as image fusion, and then from the that is build an unified representation for all those images, and then on that unified representation we do the object detection or whatever we want to do. So like these are some of the concepts which we will see in detail in the coming lectures. So in the next 3 or 4 lectures we will see some detailed applications of the of the things that we discussed today. So so we'll follow this up in the coming lectures. So till then, bye.